So in this section, we're talking about inverse functions. And I know this too is a topic that you have seen in Algebra 2. And then we sort of we touch upon it again, we reinforce a couple of steps, and we go a little bit further here. Okay, so what is an inverse relation? First of all, an inverse relation, I'm not talking about a function just yet, okay, will exist if and only if one relation contains BA whenever the other one contains AB. So if you take one relation and you consider all of the coordinate points that make up that relation, AB, right? A1, B1, A2, B2, like all of the coordinate points. And now, if for each of the coordinate points, for every single one of the coordinate points, if you switch them around to BA, right, that will make the inverse of the first relation. Okay, so you take any relation, any line like this, right? You take all of these coordinate points, okay, so the point 3, 4, the point 4, 5, and so on, and you switch around the x and y, you will get the inverse of it, basically, is what we're saying. Now, if you take a look here at the function below, you'll see that you have inverse relations here, not functions, you have inverse relations here. And if you look very closely, they're reflections of each other in the line y equals x. Okay, so what does that mean? Let's take one part of this. Let's just take this part of the blue parabola, just the right part of the blue parabola. All right? Now, take a look at that red dashed line. Do you see the red line, the dashed line? If I were to reflect that blue part, just the right part, along that red line. So how do we reflect? So suppose that red line is a mirror. Each point here, suppose I reflect it over there, right? You will see that you map out that part of the green, okay? So if you take the reflection, we're going to do lots and lots of this. If you take the reflection of this blue along this line, right? If that was a mirror, look, if this red line is a mirror, right? Then look, this point, what's the mirror image along that line? Right there. This point here, the mirror image is right there. This point here, the mirror image is right there. You will map out that other one. So the moral is we will do many examples. So two inverse relations are symmetric along the line y equals x. Okay? Now, take a look at some of the points. When you have x squared equals 4, this is the blue one, right? Here are the coordinate points for x squared minus 4. Okay? So look at this coordinate point, -3, 5. Which one exists here? 5, -3, right? For 0, -4, which one exists here? -4, 0. So how do you map one relation to its inverse? You basically just swap the x and the y. Okay? All right. Now, okay. If you find the inverse of a function, right? And the inverse is a function. How do we know if something is a function? What test does it pass? The vertical line test. If the inverse of a function is also a function, then it is called the inverse function, and we call it f inverse like this. If the inverse of something is not a function, then we can't call it f to the -1. Okay? Again, we're going to touch on all of these in more detail. All right. Not all functions have inverse functions. Okay? For example, y squared, okay, so this function here, y equals x squared minus 4. That's that blue one here. If I erase everything, y equals x squared minus 4. That's that blue graph right there. Okay? Now, the inverse of it is this green. Right? That's what happens if you take all the points and you switch x's and y's, you map out that green. Is the green the inverse of function? No. Okay? So, is the original a function? Yeah. So just because something is a function, it doesn't mean that its inverse will also be a function. All right? And there are ways to get around that. We saw in trig, when we were doing trig, remember? The sine graph didn't pass, didn't qualify. So what did we do? We had to restrict the function's domain so that the inverse would be a function, remember? Okay. Horizontal line test. We sort of touched on this with the sine. If a function can pass the horizontal line test, that means its inverse will be a function. And we say it has an inverse function. Okay? So, with something like this will pass the horizontal line test. A series of horizontal lines are drawn, and each one can only pass the graph once. Right? So this will have an inverse function. All right? Okay. So let's first start slow and see if each one of these will pass the horizontal line test and if it has an inverse function. So very quickly, get at your calculators, and here's what I want you to do. This side here, okay, you guys, I want you to graph A, and I want you guys to graph B, and I want you to tell me whether yours passes the horizontal line test. So what kind of equation is A? What kind of equation? It's a quadratic, which will give you a parabola. Will it pass the horizontal line test? No. I'm spoiling it for you guys.
Wait, horizontal.
Horizontal line test. No. Horizontal line test. It doesn't pass the horizontal line test. Does this pass the horizontal line test? It does pass the horizontal line test. So what does this mean? Yes. Furthermore, the equation A has an inverse, does not have an inverse function. B has an inverse function. Okay?
Oh, because it can be negative.
Right. No.
Yeah. Not the whole thing. I'm saying because it's to an odd exponent, that means if the number was negative, it would stay negative. But on the first one, it's
right.
Negative,
Yeah.
So
okay. So if a function passes the horizontal line test, we say it's 1-to-1. What does 1-to-1 mean? Look at the parabola here, right? Look at the parabola here. One value of y corresponds to two values of x. This is not 1-to-1. Here, each value of y, each y corresponds to 1 x. So that is 1-to-1. Okay? So functions that are 1-to-1 have an inverse function. All right? So that's a new word for you, 1-to-1. I know we see it in Algebra 2, but nobody gets it the first time they see it in Algebra 2, but this is pretty much what it means. Okay? All right. If a function is 1-to-1, here's what I mean by 1-to-1. Look at the parabola. So look, this is one value of y. Is that right? But it corresponds to two values of x. That's not 1-to-1. Here, for each value of y, there is one value of x. Okay, so if a function is 1-to-1, okay, what happens is this. So suppose you have f of x, and you know the domain and range of f of x. Now, suppose for a 1-to-1 function, you find the inverse function. Then what happens is the domain of f becomes the range of r, the range of f inverse, and the range of f becomes the domain of f inverse. Did we do this when we were doing inverse sine functions? Yeah, we did, remember? Because whereas, negative pi over 2 to pi over 2 used to be on the x-axis, then for the inverse, it was on the y-axis, right? And 1 to negative 1 was on the x-axis. All right, so between a function and its inverse, the domain and range will swap. Okay? All right. So how do we find an inverse function? This you've done in Algebra 2. First, determine whether the function even has an inverse. All right? And if it doesn't have an inverse, you could do a couple of things. You could restrict the domain like we did for the sine, right? Or you could look at other options. Now, once you determine that, okay, I'm going to find the inverse function of this, then we replace f of x with y, and then interchange x and y. You've done this in Algebra 2. We solve for y, and replace with f inverse, and then we have to state any restrictions for the domain, right? That's what we were talking about before. So let's do one here. All right, so determine whether each has an inverse. If it does, find the inverse function and state any restrictions. All right, so what's happening here is it's gradually going lower and lower and lower and lower and lower. So it's never flatlining anywhere. So we do say that it passes the horizontal line test because it's never flat anywhere. That means that this has an inverse function, and now we just have to find that inverse function. Correct. Yeah. Yeah. But like, what's a function that flatlines like that? It would be like y equals 5. Like it would be a constant function. Right. Right. Exactly. Okay. So first, what we're gonna do is we're gonna rewrite this as y equals x over 2x minus 1 because f of x and y is the same. And then you interchange x and y, right? So for each, you just swap them. So x equals y over 2y minus 1, right? I just switched x and y. Now we're going to solve for y. Okay, so x times 2y minus 1 is equal to y. We're going to distribute the x. What are we solving for? Y. So I'm going to bring all the y's to the same side, and everything with the x goes on the other side. 2xy minus y is equal to x. Now I'm going to factor out a y. And if I come up here, divide by the parenthesis, so y equals x over 2x minus 1. Okay, that is the same thing. So first of all, we're going to relabel this as f inverse of x. Remember, Precalc Honors is all about notation, form, and so on. So what do you notice here? You got the same thing back, meaning this is its own inverse. So now, does that make sense? Well, if we look at the graph again, okay, suppose you were to draw a diagonal line here through this, okay? Y equals x. So let's also graph y equals x. All right, now look, suppose y equals x is your mirror, right? We're going to reflect this around y equals x. Imagine if you cut this out on your paper, and if you were to fold your paper along y equals x, do you see how the left and the right parts would align perfectly, right? That means it's its own inverse, this one, okay? No, it's very, very rare. Yes, it's always around y equals x. So now we found the inverse. State any restrictions, right? So here x cannot equal to 1 over 2. Okay? Yes.
So if you get the same, with the same,
Uh-huh.
so it means that it's the same.
Yeah, but it's very rare that you get that. Okay, yes.
So like, let's say like there wasn't an inverse, but like you tested for one, would you get an answer? Like if you like graphed it and like you didn't see that it like didn't pass the test.
If, right.
And like you tested for an inverse, would you get an answer?
Right, but it just wouldn't be a function.
Okay.
Yeah, it wouldn't be a function. Yes.
So, on the left side,
Uh-huh.
right, you switch y with x again.
Yeah. That's how you find an inverse. So let's do this next one and you'll see, I think, if we do a couple. All right? Okay. So 2 root x minus 1. Well, let's see if, does this have an inverse function? Well, okay, so this is a square root and it's translated to the right one space, so it's right about here and it looks like that. Yeah? Okay. So obviously it has an inverse. Now, I'm just going to make some more room here. Okay? All right, so let's find the inverse of this. So first we say y equals 2x minus 1. Now, to find inverse means swap x and y. So these, we swap them, and then this will be x equals 2, y minus 1. That's what finding inverse is. Now we need to solve for x. So I take a square root. I square both sides. I need to solve for y. I square both sides. So that's going to be 4 times y minus 1. Right? And now what? Divide by 4. So x squared over 4 is equal to y minus 1. And y is x squared over 4 plus 1. But now, hang on. So now f inverse is going to be x squared over 4 plus 1. Okay, now, here we have a problem. Let's rewrite this another way of x. This is, let me write it this way. So x squared over 4 is the same as 1 over 4x squared, right? Plus 1. What is this? It's a what? It's a parabola. It's a parabola that is translated upwards by 1, right? So that's what it looks like. Is that right? But now, does our original function match with that parabola? The original function only has the positive side, right? There is no bottom side. That means we need to restrict this domain so that we only get the corresponding part to this. The corresponding part to this is just this part. Okay? So what would be the domain of that inverse so that we only take the part on the right? What should the domain be? Correct. Or, remember we always use interval notation, 0 to infinity. Okay? That way we only take the right-hand side. And if you see, if you reflect it along the line y equals x, do you see how the greens will match up? Okay? So that's inverse. Right. Okay, because the function is only this. Right? So you can only map this much of the graph, no more. Okay. So let's do this other one. Okay, so look at what this says. We have m of x is equal to x squared. So what is that? That's a parabola. But it's telling you x, that notation, that means x is a member of 0 to infinity. That means only take x values from 0 to infinity. So I erase anything that falls in the negative x's. That's that. Okay? So do you see what that is? This is another way of saying, here is a parabola, only take the right-hand side of it. Okay? That's math speak for you. All right? So now, is that something that has an inverse function? Yeah, but the one before didn't, right? That's why we restricted the domain. All right? So now we have y equals x squared. So that means x equals y squared. And now if I take a square root of both sides, I get that y equals plus or minus root x, right? But what's plus or minus root x? Plus or minus root x is this and that. So just the plus, right? So I say f inverse of x is root x. No, not f inverse, m inverse. Yeah, you gotta be consistent because, you know, we're math people. Okay?
Wait, but I thought radical x.
Okay? Yeah. Yeah. Yes. Did you have a question, Lulu? Oh, no, okay. All right, so now suppose they had said x is a member of the set negative infinity to 0, what would you have done? Only the negative part, right? Then m inverse of x would have been negative root x. Okay? Yeah. Okay. All right. Compositions of inverse functions. Okay. How do you verify that two functions are inverses? Everybody will tell me, oh, right, everybody will tell me, oh, you just find the inverse and you say, oh, look, it's no. To verify, whoops. Right, to verify, you have to find f of g of x and g of f of x. And for both of them, you have to end with x. Okay? Only then have you verified that they're inverses. So it's not that they need to equal the same thing. No, they both need to come out to x. So, right. So here, look, we're going to verify that f and g are inverses of each other. Well, this is f and this is g. So first, right? So first I find f of g of x. That means that's why we're doing what we were doing yesterday. So we're going to put g inside of f. So it's going to say the square root of x squared, yeah, minus 10x plus 33 minus 8. I love doing these. Okay? So now take a look at what happens. This is x squared minus 10x plus what? 25? No? Yeah? Huh? 33 minus 8.
Oh,
25.
Yeah, 25. So now look at what happens. I can factor this as x minus 5 squared, like that, inside the square root, plus 5. And what happens to the square root and the square? They cancel out. So you're left with x minus 5 plus 5, which is equal to what? Magic. Right? This is because they are reflective around the line y equals x. Do you see how it all fits? Like, do you see it? Do you see the beauty? This is because they are a reflection of each other around the line y equals x. So now let's do the other one. G of f of x. This is math heaven we're in right now. So g of f of x. Now, we're going to say, okay, this one's a little bit more of a doozy, but it's fun. Okay, so x minus 8 plus 5, all squared, minus 10 times x minus 8 plus 5, quantity, plus 33. Right? Did we do that right? X squared minus 10x plus 33. Yeah. Okay. Let's square this guy. I square the first term. I square the last term. In the middle, I get 2 times 5. That's 10 times the root. I'll come back to it. So basically it's a squared minus 2ab plus b squared. And then this will give me minus 10 root x minus 8 minus 50 plus 33. What happens here? Plus 10 root x minus 8 minus 10 root x minus 8 go away. So we have an x. We have a negative 8. We have a positive 25. We have a negative 50. We have a positive 33. What happens to those? They all go away. So you end with x, right? Isn't that cool? How satisfying is that? They all drop out. I think some people don't believe me that they all go away. All those numbers, yeah? They do, trust me, okay? Because they're inverses of each other and they must. All right? Yeah. Yeah, so negative 8 plus 25 minus 50 plus 33, they all go away. Okay? Yeah.
What's the x is greater than 5?
Because this is a inverse, this is a square root function, right? Where it's at like x equals 8 and 5, so it looks like that. This is a parabola, right? However, they're restricting the domain, so it can they only take like one part of the parabola and not the other. So only from only from starting at 5.
Doing the actual math is different.
Yeah, no. Because then look, that's how they look, and like again you can reflect them around y equals x. I mean, this stuff is so beautiful. Like look at how it's so beautiful. You see that? Like this only starts at the 5 and they are reflected around the y, like y equals x. Yeah.
In order to find out that they are actually inverses, you have to do both.
Yes, you have to do both. Just doing f of g of x, it doesn't matter. It doesn't, it's not enough. And suppose you did this and you did this and you got like 0 and 0. No, you have to get x and x in order for it to be inverse.
So the fact that x is greater than or equal to 5 doesn't matter?
No. So now, I know at least one occurrence of this will happen on the test. If I say on a test or a quiz or wherever, on any assessment, anywhere, verify that these two are inverses. And suppose somebody says, okay, let me find the inverse of f and show that it's the same as g, and look, they're inverses. You haven't verified, you've just demonstrated, okay? It happens, you do not get any credit for it.
So like, does it actually math?
Sure, absolutely. So if I were to find the inverse of that, so if I were to do x equals root y minus 8 plus 5 and then solve it for y, then I get this one. Yeah, but that's not verifying. Okay, this is verifying. Okay, there is always a question because, you know, there is always, like, somebody will always come and say, oh my gosh, like, my friend showed me like a quicker way to do this, Miss Malikan. And I'm like, well, that's great, but that's not what I'm asking you for. Okay, all right. Use the graph of the function to graph its inverse, right? What do we do to find inverse? We exchange x and y. So that's what we do here. So what you're going to do is you're going to take like representative points of this graph. So for example, here I have -3, 0. And what's another one? Here I have -2, -1. What's another one? 1, -2. And let's take one more. Let's take this one. 6, -3. All right. So for each of these, I swap x and y. I exchange x and y. 0, -3. So x is 0, y is -3 right there. Okay. -1, -2. X is -1, y is -2. -2, 1. And then -3, 6. Okay. And then Okay, so you know what form, like what it's going to look like, right? And that's the inverse. Does that make sense? Let's see. If I look at the line y equals x, yeah, look, they're mirrored around that line, right? So if I fold this paper along that dotted line, the original and the inverse will line up perfectly. Okay?
Yeah. So I tried to do it the other way, and just find the line. You find the line of the when you gave us.
And you found the equation?
Yeah, you found the equation. But then you do swap the x. And so I know that way it does work. When you get a parabola, how do you know which side to eliminate?
So then,
I eliminated the wrong side.
yeah. Okay, so here's what'll happen. What is the domain and range of this? So what is the range of the black, the one in the black? Here. The range is 0 to, negative infinity to 0. Okay? This is the range of this. When you find the inverse function, the domain of that inverse function has to be negative infinity to 0. So look, is the domain of that purple one negative infinity to 0? Of the purple one? What's the domain? Negative infinity to 0. So that's what you have to do. You have to find the range of this. I'm really getting excited now because this is exciting stuff. You have to find the range of this, and you have to make the range of the original the domain of your inverse. This is what inverse means. Okay? Huh? It's like you have no idea how cool it is. Okay? Like I do cartwheels and said, oh look, there's another one.
Oh wait,
yeah. Okay? Yeah. Okay, so I think you guys can handle this one on your own, yeah? Go. I'll give you a minute. Go, 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 go. What I did here, okay, so you see this, I started off with 1 point. So if you take a look at this point, right, x is 1, and then y is somewhere between 2 and 3, right? So x is 1, and then y is somewhere between 2 and 3. So I switch it to, I'm sorry, I said that the other way. X is somewhere between 2 and 3, and then y is 1. So if I switch that, I say, okay, x is 1, and y is somewhere between 2 and 3, okay? So that's just like a starting point. And now, take a look at this. If this business about inverses is interchanging x and y, right? Where does this look like it has an asymptote? At the y-axis, right? Yeah, at the negative y-axis. So the inverse will have an asymptote at the negative x-axis. Okay? And now look, what's happening here? It looks like it's sort of like leveling off at y equals 2. So this will sort of level off at x equals 2, right? So if this is y equals 2, this will be x equals 2. And so I know that there is an asymptote here and an asymptote there, so it'll look like that. Okay? All right, so this for tomorrow.